So guys, next session, I'm gonna come up with something much better. I'm gonna probably do Google Meeting or something and figure out how to record. This is so messy and I apologize. Okay, I think we have retained 2 people. So, Lavon, do you want to join again? I don't want to take up more of your time, so I'm just gonna start. Okay. Anyways, the flight time, where were we? Oh, we're reviewing X and Y motion. Okay, so that was the demonstration with the little hair tie. And so as you saw, everything kind of slowed at the tippity top, and that's what happens. Basically, because our motion's moving up and gravitational acceleration is pointing down, what we have is deceleration. And we just decelerate to the point where it's 0, and then it's going to go down again, at which point our velocity is going in the same direction as our acceleration, and we're going to speed up. And so in this case, it's going to be 0 at the highest point, and then we're going to go faster when our acceleration is with our velocity. And x, what I love about x is x always stays the same, right? So our velocity is constant for x. And because we have constant velocity at every single point in terms of the horizontal component, it means that if there's no change in velocity, there is no acceleration to be had. And so VO x will always equal VF, or V final x, V whatever you want to say, Vx. And that means AX is always going to be equal to 0 meters per second squared. Okay. With that knowledge, let's walk into step A, right? So I said list what I know and don't know. In this case, I'm looking for time. So I have time with a question mark. And then I have our initial velocity. Our initial velocity is 40 meters per second, and take this with a grain of salt, because whenever they say initial velocity, you automatically see in the visual that it's going to be this initial velocity, right? We have our velocity triangle, velocity right triangle, and we still have, that means we have a VOY and we have a VOX that are yet to be solved. And so we also have acceleration. We have presumed acceleration in terms of, oh, okay, let me backtrack this. I don't like how I'm explaining this. What I'm going to do is list what I do and don't know, but in terms of X factors, Y factors, and ones that don't matter where they are. So I'm actually going to make a table. I should have made this earlier, my bad. I have X factors, and I have my Y factors, and I have what I call like the mid, like it doesn't matter where it goes because it's the same in both. And so once again, we talk about our mid, right? So this is kind of like our resultant. So I'm going to say 40 meters per second. I'm going to say time is here too, because time is the same in both X and Y. Our Y factors, once again, I'm going to draw that triangle that we had earlier for VO, 40 meters per second. And we know we have VOY and VOX. And this angle is 30 degrees. Okay. And so if we do think about it, we do know VOY, because we look at this is our opposite, and we have our hypotenuse. So opposite of our hypotenuse is going to be sine. It's going to be 40 sine 30. I am taking shortcuts with not setting up opposite of our hypotenuse, by the way. So if you need any clarification, just ask me. And the VOX is just going to be that same thing with cosine. If it's not sine, it's cosine. So VOY is going to be 40 sine 30 VOX, 40 cosine 30. We also know that, like we were talking about earlier, our x is going to stay, our acceleration, the x is going to be 0 meters per second squared. We don't have our change in x, no stitching. We have our acceleration in y, which we know is always going to be the same factor because of free fall. And this is something you've seen in the lab multiple times. And we actually do have our change in y. Our change in y. And so it's going to be our final minus our initial, right? And in this case, it's important to notice because often I'll see like this, people put change in y, 25 meters. And yes, 25 meters. But you always remember that change in y is going to be equal to yf minus y initial. In this case, y final is going to be at the floor. So it's going to be 0 minus what we started off at, which was like 25 meters. So change in y is actually going to be negative 25 meters. That's just something to keep in your head. So let's finally solve our problem that we have everything laid out for like this problem and beyond. So we're going to solve for part A. So what is the flight time of the cannonball? So since time is on our middle category and it really is going to stay, we can solve it's in our middle category. We can solve our time with both the x or the y factors. In this case, though, we need to ask ourselves, what do we have more of? What do we have enough to draw from? And in this case, if you look at it, we don't have change in x, but we have change in y. And so our y factors are more plentiful and more bountiful. They're inviting us, right? And so we are going to use the y to solve for time. And all that includes is really looking at your formula sheets and the adjusting in what's it called out. Oh, the English just slipped my mind. And changing up that formula to fit what you're doing. So let me show you. So third is I find my formula. Find what formula fits. What equation fits. In this case, I'm going to be using this equation and I'm going to write it because this is how it probably appears in your textbook and what you'll have written out on the page. It's going to be change in x is equal to VOT plus half AT squared. Now I'm going to do this, but I'm going to adjust it and I really forgot that word. And do it to the point where we can solve for our y factors, right? So we're not thinking about x. We're thinking about change in y is equal to not just initial velocity, but initial velocity in the y direction times time, because time is great. We don't have to adjust it, plus half ay, right? Acceleration in the y direction times t squared. And so all you got to do is plug everything in now. So 40 sine 30 times time plus half, negative 9.8 t squared. In this case, you do have to solve for a quadratic. You have to use the quadratic formula to solve. Usually there's a setup in your calculator that you can program to make it solve for quadratic. I don't know, like if you see, I put in my third. Okay, never mind. But in the program for my calculator, I have like quad solve. Just do quadratic formula. You don't even have to plug it in. You just have to show her that you are using the quadratic formula. And so in my, I would write like negative b plus minus b squared minus 4ac over 2a. And once you plug this into your quadratic, you'll get a positive and negative value. And the answer is going to be your positive value, so negative 5.8 seconds. I hope she doesn't ask you a quadratic on exam day. I feel like it's not very important. I just don't understand the point of it because we're doing physics, not math. But in any case, just be prepared for it or be prepared to how you're going to show your work for it. So that was part A. Next is part B, which is what is the range of a cannonball? And so we're at 7:35. I'm going to give y'all like 3 minutes to set up and try to find an equation and see what you're going to use for the range. Okay, so I'm going to set a timer for 3 minutes. And just holler at me if you have any questions or put it in the chat. Okay, so that was 3 minutes. Sorry, y'all. I'm gonna hear the timer. I love the timer. But anyways, so I hope that y'all got set this up somewhat or found an equation that somewhat works with this. I'm just gonna jump right into it. And so our question is, what is change in x, right? And it kind of comes back to this table right here again. And if we think about what we have in terms of x, we have these three kind of variables right now. And if we look at our equation chart, then perhaps you will see, I'm trying to find my equation charts, which is this very generic formula, VT. So this is what is probably showing up in the textbook or on online when you're looking up for kinematics equations. We're just going to change this to better fit what we have. And so change in x is going to be equal to Vx times t. And ultimately, it doesn't matter if you do Vox or Vx, because if we remember from our conceptual learning, the V initial x is going to be equal to the final Vx anyways. The velocity of x is always the same. The horizontal component of velocity is always the same. And so in this case, we just have to make sure we solve for it. And we did, we solved for it right here. So now we're just going to carry that down. 40 cosine 30 times t, which we saw from earlier, 5.08 seconds. But let me add that, 5.08 seconds. Okay. And so once we plug this in, then we have our answer, which I think I plugged it in, 175.98 meters. So see, everything is so smooth flowing once you have it set up. For kinematics, that is the hardest part. It's just listing your variables, knowing what you have. But I really do think this table helps kind of see where you need to start. I think starting it is the hardest part. And after that, it's just like nice and easy plug and chug, right? So our last one is questions, not our last one, actually, not our last one, is C. So they're asking, what is the impact velocity when the cannonball strikes the ground? And we're supposed to include both magnitude and direction. This problem, I will admit, is much harder than the previous two ones. This is kind of like a accumulation of what you've been doing in parts A and B. And so for this one, you probably need longer than 3 minutes. I'm just gonna give you 3 minutes to set up though, so that we can kind of go through it at a good rate. So I'm gonna start a 3 minute timer and let's work through this. Okay, so back at it. This one is challenging, I feel, because it's very multifaceted. You're using kinematics in kinematics. You're using kinematics in, what you might call it, in vector addition, basically. And so we start off as I kind of copy pasted and then I added in our new variables and we also redrew our triangle, right? So as you see, final velocity is actually one of these values. It's in the middle and it's going to be reliant on a couple of things. And so if I drew this triangle here, right, think about the picture of the little ball falling down, right? It's falling down at an angle. And although they're asking us that final velocity, but we can't directly solve for that final velocity. We're going to have to solve for its components. So that means the x and the y, right? So we have the x. X is my favorite part. I told y'all it's like my favorite child because it stays the same, right? In this case, it's still going to be 40 cosine 30 throughout. What's giving us trouble is going to be the v final y, the final velocity, the y component of the final velocity, a mouthful. In order to solve this, we have to use kinematics, right? Oh, I'm so sorry. And when we're using kinematics, to find it, we can really only use things that are in this column to solve for other things, to solve for that, because it's a y component. Okay. And so we can just use, you can really just look for any formula that has what you have here and also has what you need to solve for. In this case, I use this one. B is equal to VO plus AT. And I just kind of adjusted it for our situation, which was V final Y is equal to V initial Y plus AT. Okay, or AYT if you want to be really specific. So if you do this, what you do is you get, remember VOY, if we look back at VOY, where are we getting that value from? Get it from here. So we're just going to copy it here. 40 sine 30 plus A, so negative 9.8 meters per second, times, oh, well, there's something there, okay, times T 5.08 seconds, okay? And so once you put this all together, I'm going to skip the math. I'm just going to give you the answer right away. It's going to be negative 29.78 meters per second. To put a loop circle around that. So once we redraw our triangle, make it a little bit bigger. I feel like if it's bigger, it's just easier to see, easier to work with. 40 cosine 30. And VFY is equal to negative 29.78. And like Lavon said earlier, we're just kind of going to do Pythagorean for this. Again, we see Pythagorean a lot in this case. And so a squared plus b squared is equal to c squared. So you're just going to do, I'm too lazy to plug this in. I don't know why, but just do whatever you need to do. Negative 29.78 squared is equal to c squared. And to get the answer, you're just going to square root all of this after you've already squared it, of course. And this is going to give you a final velocity of 45.68 meters per second. And as we said earlier, we can't stop here because we need both a magnitude. And so we're just going to use our tangent once again. Our angle is equal to our inverse tangent of y over x. So y over x, so negative 29.78 divided by 40 cosine 30, or whatever that value is. That should get you an angle of negative 40.69. Okay, and that is your answer. So this is probably the hardest one of the three. And what we're going to move on next to is motion graphs. So motion graphs are, I'm just going to create a little graph for the motion graph so that you can kind of think about it, okay? So I'm going to set it up, but as I'm setting it up, think about what it's asking you and how you would sketch it. And then after I finish setting up, like we'll just go through it. Okay, so I'm just going to set it up. D. I should have done this earlier, so I apologize. or whatever, right? So time, and put my papers, time. It's a little bit of a weird graph. I could just put the numbers here too, but I'm just gonna do that. So this is gonna be our vertical velocity versus time. I can just navigate this like this. How cool. All right. Sorry, I'm doing a very rough draft, but y'all can kind of, I hope y'all can kind of see where we're going. It's supposed to be a beautiful grid for your reference. It is not because I'm drawing it. Okay, so we're gonna do number, not D, not number, but letter D. So it says to sketch the horizontal velocity versus time and the vertical velocity of the projectile versus time. So we talked about horizontal velocity earlier, and we talked about how it's my favorite. But we're going to do this in context of the problem. So you kind of, you know that it's going to be the same, but we had to go back to what we solved for. So I'm going to go back as this little table, and I see right here that I put horizontal velocity as 40 cosine 30. So I guess I have to solve it, 40 cosine 30. I've been off putting it all along. So 40 cosine 30, that gives us 34.6. I'm going to round that up to like 35. And since we know, okay, so think about it, right? So at time one, it's the horizontal velocity is going to stay the same. We think about this. It was the same at every single point on the line. So it's going to remain constant at 35, okay? So that's how we graph that. So next is we're sketching the vertical velocity of the projectile versus time. So vertical velocity, of course, is going to be more challenging, right? But we know something right away. We know that if we think about this, what we talked about earlier is that at the tippity top, it's got to be 0 meters. It's got to be 0 meters per second. And so if you look at the time, you can assume that halfway it's going to be at 0. So our time, now let's not do that actually. So our initial velocity was in the y direction. So we go to our y factors right here. It's going to be 40 sine 30. So we start off with 20. So I'm going to do 20 somewhere here. 20, and then at time 5, we know that we end up with VFY of negative 30. So 5 is going to be negative 30. So all the way down here. And so we can just connect these dots. You can also do more dots between, but it's just trying to make sure you understand that things are happening and that you recognize that there's this pattern going on. All right, that was super vague, my bad. Oh, I didn't leave space. Okay. So, okay, so I'm so sorry. I'm like out of space. I'm just gonna sketch it in a different color. All right, so next we have the horizontal acceleration. So our horizontal acceleration, I'm gonna sketch it really vaguely. If we have, remember what we talked about earlier when we said horizontal velocity is not changing. So if it's not changing, there's no acceleration. Acceleration is gonna be at 0. Whatever you do for this this AXT graph, it's gonna be here at the 0 line. For here, it's not gonna be 0. Right, but if we think about, I don't know if y'all took calculus, but the tangent of the slope, based at that's not tangent of slope. But if this line is kind of diagonal, it's going to be straight when we're taking the derivative or we're going down a graph, right? So all we got to do is take the slope of this line. I think the slope was about negative 10 because it's downwards. And so at negative 10, are we just going to, all we will do is just put like a line here, and that's how we graph for acceleration of y versus t. So pretty straightforward. It does get just, it tests your understanding. Okay, we have about 4 minutes left. This is an additional problem for 2D kinematics. I will solve it before the after the end of our meeting and just post it up with the annotated slides. And so the last one that we have really is this. Actually, since we have like 10 minutes left before the meeting ends, is there any questions or any resources that y'all would like to request for me to share before the exam on Wednesday?
So for the last problem, um, for part C, so how do you know when to use kinematics equation? Instead of using that, would it be wrong if I just use um the x value and y value, which is 40 sine of 40 sine 30, or
Oh,
do I
okay.
have to do the kinet? You know what I'm trying to
I
say?
see what you're trying to say.
Okay, yeah,
So
okay, yeah.
So the reason why we can't use 40 sine 30 at the moment is because remember when we were doing from this triangle earlier, this triangle up here, the 40 comes from somewhere. The 40 comes from this long side of the hypotenuse. And so in this case, we can't use it down here because that long side is going to be a completely different value. So we can't really kind of transfer it over. Like, I know what you're talking about because when you're talking about like a perfect projectile motion, that's just like this. It starts off at the ground and it ends at the ground. What will be at the beginning will be at the end. So in that case, you can use the same because the angle is going to be the same. So this would be 40 and this would be 40, right? That's in a perfect scenario. However, this is off a cliff. So what we're starting off with is at a different angle than what we're ending with, which is also going to be at a different angle. So because we have to kind of factor for that, we can't use the same, like we can't use 40 sine 30. Does that make sense?
Yeah, that makes sense. I get it. Okay,
Okay.
thank you.
But yeah. Any more questions? That was a good question. Anything else? All right. Okay. So we have like 8 minutes left. So let's do this friction problem. I think it's a good problem because I think for at least one component of a question, she's going to ask about friction. I'd be surprised if she didn't. So in this case, since we have a little time left, I'm going to give about 3 minutes to work on it and then we'll walk over it together. Or 2 minutes. Actually, let's just walk over it together. Okay, a worker pulls a 20 kilogram packing crate at a constant velocity. So 20 kilograms, constant velocity across a rough floor. Also important detail. A force of 55 newtons is being applied to the crate at an angle of 35 degrees below the horizontal. Our first question is to draw the free body diagram. Okay. So I go find my notes for this problem. I think I left them. Sorry. Anyways, I'll just draw and look for my notes later. So a worker pulls a 20 kilogram packing crate. So you have our mass, and we know that it's 20 kilograms. We know constant velocity, and the reason why I highlighted constant velocity is it indicates no acceleration. So AX equals 0 meters per second squared. Okay, and the rough floor indicates there's some kind of friction. There's some kind of friction force. And then we're also told that a force of 55 is being applied to the crate at an angle of 35 degrees below the horizontal. So if this was the horizontal, then someone is pushing this crate. And it's 35 degrees below the horizontal. So if we were drawing a free body diagram, then we'd assume that force kind of carries on, if that makes any sense. I'm still trying to find it. Okay, so we assume that force carries on to kind of our free body diagram. So this is going to be our free body diagram. It's sitting on a surface, so this is force push or whatever you want to say. We got force normal. We have force gravity or weight, whatever you want to call it. And we have force friction because they told us that there was a rough floor. Okay, so there's a lot of things going on. So we have our A points. We have our points for part A. Good job, right? So what's the force of friction between the crate and the floor? Okay, so this is pretty heavy, but not that heavy, right? I don't think it's too bad if you just break it down the right way. And so first, let's talk about our force friction. What axis is it on, right? If we look at it, we see that it's on the x-axis. What axis? X-axis. So that means we only care about forces in the x direction when we're solving for this. So that means we care about this. But first, if we look at our graph, we see that something sticks out. Something is not right. And that's something that's not right is this force push. This is an ew, right? We don't like that force push. We want to break it up like we did earlier on that slope with into the x and the y components. And so I'm going to redraw this with everything broken down. Oh, and something I didn't include is the angle, 35 degrees. My bad. So this is 35 degrees. And this is our x and y components, right? This is force push x. This is force push y. Okay. And so force newtons. I mean, force normal. And then we know that we also have force gravity. We also know that we have another force going down, which is force push y. And then we also know that we have a force going this way, force push x. Okay. And so if we only care about our forces in the x direction when we're solving for this, that's the only thing we had to consider, right? So if we want to find the force of friction between the crate and the floor, the only things that we can actually use are really, I apologize. If we want to solve for force friction and we're only given two forces on the x-axis, then we can use them to solve for each other. Huh. Let me write that again. Okay, I'm gonna draw it out. I feel like if I write it out, it'll make sense. So it's kind of like this relationship between the forces. It's hard to explain. Okay. So F net x, we know that sum of forces in the x direction is equal to mass times acceleration. I'm running out of time. Okay. And so this is going to be force push x, because this is our positive minus our negative, right? So I mean, so minus FF is going to be equal to mass, which is 20 kilograms times acceleration. Our acceleration, however, is 0 because it is at constant velocity. So this automatically goes to 0. Once that goes to 0, we have FPX is minus FF is equal to 0. And what we can do is we can make them equal to each other. So FPX is going to be equal to FF, right? That means what that tells us, if we solve for FPX, we solve for FF. Let me go explain this. If we solve for the x component of force, the pushing force, then we solve for friction force as well. And so since we have that angle for friction for the push force, we can actually solve for the push force in this case, right? So look at this. This is angle 35. If we're told that force is 55 newtons here, which I'm so sorry I did not write, 55 newtons, then we can actually solve for this x right here, which is 55. This is adjacent, so 55 cosine 35. And this is going to be equal to 55 sine 35. Okay. And so if we have this and we said that it's equal to that, then 55 cosine 35 is going to be equal to our force friction. If we solve this into the calculator, that will be our final answer. So that is all. That is all there is to it, right? But it's that setting up that is hard, of course. And then our second question is, what is the coefficient of kinetic friction on that floor? And so kinetic friction is this formula. So just write this on your formula chart. It's going to be F. Okay, after this meeting ends, I probably will just end the meeting. But if you have any questions, feel free to DM me. I'm going to send out the annotated slides right away. I will also put the recordings onto YouTube so y'all can watch if y'all want to watch again. But all the annotated slides will be on there and anyone can just DM me questions. Thank you, Danny. That helps. All right.